So last time we ended up concluding that the force is minus 2 pi g little m a squared sigma k hat integral from theta equals 0 to pi in a quantity that involves a function of theta. So there's cosine theta, we have sine of theta. We're dividing by the little r squared, which in terms of theta looks like this. Actually, we have a unit vector as well, so we ended up with a 3/2 d theta. If I remember correctly, there's often that 3/2, and I mean, we could do this integral in terms of theta. I'm not sure. That seems a little bit involved. It's perhaps easier to change variable to little r, which is this thing. Actually, no, not quite. It's let's see, little r squared is big R squared plus little a squared minus 2ar cosine of theta. And so we can say that 2r dr is equal to, we take derivatives of these, there's only theta to take derivatives with respect to, and so here we get 0, and we end up with, that's equal to 2a big R sine theta. We had a minus sign from the cosine, and so we get d theta. And so we can change variables to this. We have to replace things like a cosine theta. So a cosine theta reads r squared plus a squared minus little r squared over 2 big R, r minus a cosine theta. Therefore, that object is equal to big R minus big R squared plus a squared minus little r squared over 2r. And this is equal to little r squared, positive, minus a squared plus big R squared over 2r, big R. And so our integral becomes, so our force is an integral minus pi g m a sigma k hat over r squared, integral of 1 plus r squared minus a squared over little r squared in dr. And notice that when theta is equal to 0, we get that little r squared is equal to, little r squared is equal to a squared plus a big R squared minus 2a big R. That's the same thing as r minus a squared. And so r is big R minus a. Sorry, little r is big R minus a. Right, so little r is r minus a as a result of that. And when theta, because we were going from theta equals 0 to theta equals pi, so when theta is equal to pi, we have r squared, we have a different sign, right? So we have a squared plus r squared plus 2ar, and this is just a plus, so it's big R plus a squared, and so this becomes r plus a. And so we're integrating from big R minus a to big R plus a. And this is straightforward. So this thing becomes minus 4 pi g a squared sigma little m over big R squared k hat. Okay, and evaluate that straightforward. Here we just get r. And here he has 1 over r squared. In both cases, we have to integrate from here to there. We end up here, and notice that 4 pi a squared is the area of the surface on which there is a mass density, sigma. So 4 pi a squared sigma is the mass m. So we get minus g little m times big M k hat over big R squared. Unsurprisingly, it's as if all the mass were at a point, and we have a distance r between these two.